last time we had seen what are scalar quantities versus what are vector quantities. Vector quantities or vector physical quantities are those quantities that have both magnitude and direction, like force, velocity, displacement, and so on. Now, we have a new quantity called the vector quantity. So we should be able to use this. We should be able to apply mathematics to this, right? So if you're dealing with vectors, you have to use vector algebra. Now, this behaves slightly different than the normal algebra that you've studied using variables. In essence, vector quantities are intrinsically different from scalar quantities. That is why vector algebra is also slightly different. How to add two vectors, how to multiply two vectors, they would follow certain rules which you have not seen till now. So these would be new for you. Anyway, before we get on with vector algebra, we should know how to represent that first. We're going to look at two types of vector representation. One is going to be the geometric representation, and the other would be the algebraic representation. In vector algebra, you would be using this, okay? Of course, you would need an understanding of this in order to apply this. Well, let's take a look. We have seen earlier that vectors are represented by, diagrammatically, they're represented by an arrow. The head of the arrow, it shows the direction, and the length shows the magnitude, okay? This is the magnitude. If this length is, let's say, 10 units, and this is the force we are measuring, we can say this force is 10 Newton. In which direction? In this direction, of course, in this direction, okay? So that is how vectors are represented diagrammatically or geometrically. So imagine this to be the room, right? One of the corners of the room is this origin, and this length, the right side, this edge of the room represents the x-axis, the vertical edge of the room represents the y-axis, and the edge moving towards you, that is the z-axis. That is what we've drawn. This object here, it's at some position here, okay? So how do I get the position vector of this? The position vector of this would be a vector, an imaginary ray joining from the origin to this point. Now, algebraically, a vector would be represented by a letter, just like we use in algebra. Let's use R for that, okay? But then, what is the difference between a normal variable and a vector? It's this arrow, okay? A small arrow on top of this. So algebraically, vectors are represented like, you can use the variables like a, b, x, y, z that you used to use normally in algebra. But here, in order to indicate that this is a vector variable, you use this arrow. This is one way to represent. Sometimes some books will just represent this. A bar, that also means a vector. A vector actually contains two types of information. One is, what is the magnitude of the vector? So modulus of a vector, this thing is what is magnitude, okay? And it also contains the information about the direction. So a hat or a cap, this thing is a unit vector in the direction of the original vector A. Okay, unit vector is a small vector of length 1. So if I ask you what is the unit vector in the direction of this vector, you can draw something like this. You can say draw a 1 centimeter line. Like this. Okay, so this is a unit vector in its direction. So the magnitude of the vector multiplied by the unit vector gives you the entire vector. This is the algebraic representation of a vector. Vector A is equal to magnitude of vector A multiplied by direction of vector A. Okay, so this is how you represent it algebraically. Now the question would be, what is unit vector? This is something new for me. So the unit vector is defined like this. We use the same definition. A hat, or the unit vector, would be given as this upon modulus of. Okay, we just bring this side. So the original vector, when you divide it by its magnitude, you get a unit vector. Some basics of vector representation. Okay, algebraically we denote like this. Now, what does this mean geometrically? Let's take a look at that also. Okay, let's consider that this is a 10 Newton force, the bigger one. Okay, if I want a 1 Newton force, what would I have to do? See, the direction is the same. I do not need to disturb the direction. The direction is the same. If I just divide this into 10 small parts and just choose one small part, wouldn't that be a 1 Newton vector in the same direction? And that is what we are doing here. Original vector, let's call this vector A this time, okay? Vector A. If I divide vector A by 10, would I not get the unit vector in the same direction? Would I not get A cap? I would, right? Now, let's learn some basics of vector operation, okay? If I have a vector A, how would you represent vector 2 times A geometrically? How would 2A look like? 2 is just a number, a scalar number multiplied with my vector. So what has changed? Has the direction of the vector changed? 2 times A, has the direction changed? No. Direction is the same. So in the same direction, you draw double the length. This is your 2 times A vector. Okay. 5 times A, again, just increase the magnitude in the same direction. That would be 5 times A. So if you're multiplying scalar numbers to the original vector, just the magnitude keeps on increasing or decreasing depending on what number you are multiplying. So if I say 0.5A, what would that be? It would be half of this, yeah, this vector. So if we multiply or divide a vector by a scalar quantity, this is how it changes, right? How to add a scalar quantity to a vector quantity? Can we do that? Addition of vectors. Is this possible? Think about this. A scalar quantity, can you add it to a vector quantity? Is this possible? While you are thinking about it, think about this also. Can you add mass to volume? The answer is no. See, both the quantities have to be of a similar nature in order to be added or subtracted. Multiplication is another thing, but addition happens only between similar quantities. So mass can be added to mass. Mass cannot be added to volume. Similarly, scalar quantities can be added to scalar quantities only, not to vector quantities. So this is not even possible. You cannot add a scalar quantity to a vector quantity. Okay. So does that mean there is no addition in vectors? Well, there is. We can add vectors to vectors. Let's take a look at how to do that. So now we're going to take a look at addition of vector quantities. The simplest example is addition of two vectors, vector P and Q. Note that if you learn about addition of vectors, subtraction of vectors is the same thing with slight difference. I'll just quickly tell you that difference. See, vector P plus vector Q. This is how you add two vectors. Yeah. If you have to subtract vectors, you would do P minus Q, correct? I told you that if you know how to add, you basically know how to subtract. Because I can say that instead of P minus Q, I can say that what I'm doing actually is I'm adding these two vectors. Am I right or not? I'm adding these two vectors. I'm adding a vector P and another vector minus Q. It's same as saying I'm doing P minus Q. So, in a sense, if you learn how to add, you basically know how to subtract also. So, pay close attention now. We're going to learn how to add two vectors. As you can see, we have two vectors here, vector P and vector Q, and we are going to add those two vectors. There are different ways to do that. First, what is called the triangle way or the triangle law of vector addition. In this, what you do is you join the two vectors head to tail. So if we have to do P plus Q, triangle law says that you first rearrange the two vectors. How to rearrange? Bring the second vector on top of the head of the first vector. So the tail of the second vector, this is the tail of the second vector, this is the head of the second vector. This is the head, this is the tail. Bring the tail of the second vector on top of the head of the first vector. How can I do that? You have to do it without rotating the second vector, okay? So what you can do is you can move this thing and like you can pan this around a 2D plane and the vector value will not change. So instead of drawing it here, we can draw it here, no problem at all, okay? So now this is also your Q vector. So first step is done for triangle law is the rearrangement of vectors. I have rearranged the two vectors. P was already there, I did not disturb it. Q, I brought it from here to here. Now you forget about this, okay? You forget about this. This is one vector, this is one vector. Triangle law of vector addition says that the sum of these two vectors is going to be the third side of this triangle. That will give you the magnitude of P plus Q. What about the direction of the two vectors? So look at the order in which we are going. We are going in anti-clockwise direction. From this point towards the head, and then from this point towards the head of vector Q. I'm going in this direction, right? So my order is anti-clockwise. The sum of these two vectors is the line joining the tail of the first vector to the head of the first vector in the opposite order, okay? So not in the same anti-clockwise order, no, but in the opposite order, like this. So this arrow, this ray represents vector P plus Q. How to calculate the magnitude, how to find what is the direction, what is this angle. These are some things that you will learn later, okay? That will keep for later. For now, a quick recap of what we did in triangle law of vector addition. First thing, we moved the second vector, we rearranged the second vector so that the tail of the second vector sat on top of the head of the first vector. After doing that rearrangement, triangle law says that this line gives you the magnitude and this should be the direction if you are adding the two vectors. That is it. That is the summary of the triangle law. Let's take a look at the parallelogram law of vector addition. See, these two laws, triangle and parallelogram law, they give the same result. Okay, these are two different ways of adding. So let's now look at the parallelogram law of vector addition. So parallelogram law of vector addition. They also say that you have to first rearrange the vectors, but this rearrangement would be slightly different than the triangle law. In parallelogram law, we have to rearrange the two vectors so that their tails coincide. The tails are joined at the same point, which is already the case here, right? Tail of the first vector, tail of the second vector already joined. So no rearrangement necessary in this case. It's already done for you. Okay. What after that? After you've made sure that their tails are coinciding, that the vectors are nicely arranged or rearranged, you draw a complete parallelogram. You draw this, you draw this. After that, the leading diagonal of this parallelogram, not this diagonal, no, the leading diagonal gives you P plus Q, gives you P plus Q, vector P plus vector Q. Again, what is the magnitude of this? How long is this? That means, or what is this angle? We'll do that later when we study about vectors in detail. For now, just few things to keep in mind. Vector algebra is different from scalar algebra. And we've started with showing that how vector addition is different from scalar addition. In vector addition, the angle between two vectors also comes into picture. So adding vector P plus vector Q is different from adding vector P plus vector Q. Okay? Even though their lengths may match, but the angle, there is some angle, no? So that's why. So angle also comes into picture. That is why vector addition is different than scalar addition. Then we saw two laws, triangle law and parallelogram law. Basically, these are methods to add vectors. Similarly, you will see how to multiply two vectors, okay? How to multiply a scalar to a vector, that we've already seen. Multiplication also, or the product of two vectors, is also of two types. One is called the scalar product, the other is called the vector product. You're going to learn about those things later.